Hello, everyone, and welcome. Today, we're diving into a topic that is, quite literally, all around you: electrochemistry. We're going to break down the essentials, making sure you get a solid grip on all the key concepts for your class. I mean, think about it for a second. Your phone, your remote, your earbuds. How does a tiny little battery power all of that? Well, it's all down to chemical reactions, and we're about to uncover the science behind that magic, figuring out exactly what's going on inside those little power sources. Okay, so here's our game plan for today. First, we'll cover the basics. What even is electrochemistry? Then we'll look at how electricity can flow through a liquid. After that, we get to the fun stuff, making electricity with galvanic cells, and then using electricity with electrolytic cells. We'll even see how to produce a cell's power, and finally, we'll connect it all back to the batteries you use every single day. All right, let's kick things off. So, what is this all about? We're getting right to the core idea, the very spark of electrochemistry. Okay, so here it is in a nutshell. Electrochemistry is basically a two-way street for energy. On one side, you've got chemical reactions creating electricity, like in a battery. And on the other side, you've got electricity making chemical reactions happen, reactions that wouldn't just start on their own. It's all about swapping between chemical and electrical energy. That's the whole game. So before we can really understand how a battery works, we have to figure something out first. How in the world does electricity move through a liquid? Because, well, it's definitely not the same as electricity just zipping through a copper wire. And this is a really critical point. In a metal wire, you've got what's called a sea of electrons just flowing along carrying the current. Simple enough. But in a solution, it's not the electrons themselves that are doing the traveling. Instead, you have these charged particles, these ions, that are physically swimming through the liquid. They're the ones carrying the charge. So you actually have matter moving, which is a huge difference. To talk about this properly, we've got to get some terminology straight. First up, resistance. It's just what it sounds like. It opposes the flow of current. The exact opposite is conductance, which is how easily the current flows. Then there's conductivity, which standardizes that measurement for a specific little cube of solution. And the stuff that makes this all possible, we call those electrolytes. These terms are our building blocks for what's coming next. So that brings up a question, right? If conductivity is just for a tiny, specific volume, how do we compare different substances fairly? Well, that's where molar conductivity comes in. You can think of it as the great equalizer. It levels the playing field because it measures the conducting power you get from exactly 1 mole of a substance. This way, we can make a true apples-to-apples comparison. And here's the formula that ties it all together. This is a big one. Molar conductivity, or lambda m, equals 1,000 times K, that's conductivity, divided by C, the concentration. You are definitely going to want to remember this one. It's absolutely essential for solving problems. Now this next part, Kohlrausch's law, sounds a bit intimidating, but the idea is actually pretty genius. Imagine a solution that is so dilute that the ions are basically social distancing. They're too far apart to interact. In that situation, each ion just does its own thing and contributes its own specific little bit to the total conductivity. And why is this so cool? Because it gives us a clever workaround to calculate values for weak electrolytes, which are otherwise super hard to measure. All right, we've laid the groundwork. Now for the really cool part. How do we actually make electricity from chemistry? Let's dive into galvanic cells. These are the engines inside most of the batteries you use every day. So what is a galvanic cell? It's basically a device that takes a chemical reaction that wants to happen anyway, a spontaneous reaction, and it captures the energy. It forces the electrons to travel through an external wire, and boom, you've got electricity. A key thing to remember here, the anode is the source of electrons, so it's negative, and the cathode is where they're headed, so it's positive. Now, chemists don't want to draw a whole diagram every single time, so we use this shorthand notation. It's super simple once you get it. Anode is always on the left, cathode on the right. That single vertical line, that just means you're going from a solid to a liquid or some other phase change. And that double line in the middle, that's the all-important salt bridge, the connector that completes the circuit. Okay, so that's how we get energy out of reactions that happen naturally. But what if you want to do the opposite? What if you want to force a reaction to happen that really doesn't want to? Well, for that, you need to put energy in, and you do it with an electrolytic cell. This chart right here is gold. It lays out the differences perfectly. A galvanic cell, spontaneous reaction, makes electricity. An electrolytic cell, non-spontaneous, uses electricity. But look closely at the signs of the electrodes. They're flipped. This comparison is a classic exam question, so you'll definitely want to lock this information in. Okay, so you're using electricity to make something. But how much can you make? That's where Faraday's laws come in, and trust me, it's just a simple 4-step recipe. Step 1, figure out the total charge. Step 2, convert that charge into moles of electrons. Step 3, use the mole ratio from your balanced equation. And step 4, convert the moles of your product into its mass in grams. That's it. Just follow the steps. So we know these cells can make electricity, but how much? What actually determines the voltage you get from a battery? Well, there are formulas for that, and that's exactly what we're going to look at now, how to predict a cell's power. All right, let's start with what we call standard conditions. That's just an ideal lab setup. In this perfect world, the cell's voltage is super easy to calculate. It's just the potential of the cathode minus the potential of the anode. You can think of it as a measure of the pull on the electrons. The bigger that difference, the more oomph you get, and the higher the voltage. But let's be real, the world isn't usually standard. So what happens then? That's where the famous Nernst equation comes to the rescue. It's our real-world formula. You start with that ideal standard potential, and then you use the Nernst equation to tweak it based on the actual temperature and concentrations. It's how you find out the actual voltage a cell is producing at any given moment. And this is where it all connects back to the big picture of chemistry, thermodynamics. Remember Gibbs free energy, or delta G? That's our ultimate test for whether a reaction will happen on its own. Well, this beautiful little formula links it directly to the cell potential. If your cell potential, E0, is a positive number, then your delta G has to be negative. And a negative delta G means, you guessed it, the reaction is spontaneous. It's a perfect connection. Okay, let's bring all this theory back down to earth. Let's take it out of the textbook and put it right into your daily life. Because these principles aren't just abstract ideas. They are, quite literally, everywhere. The battery in your remote, that's probably a dry cell. The massive one under the hood of your car, that's a lead storage battery. That tiny little button cell in a watch could be a mercury cell. They're all galvanic cells, but each one is engineered with a specific chemistry for a specific job, whether it's a big burst of power or a slow, steady trickle of energy for years. So you see, this chapter isn't just about passing your next exam. The principles of electrochemistry are at the very heart of our future. As we push towards electric cars and green energy, the big question is, what will the next generation of electrochemical cells look like? The science we've talked about today is exactly what will provide the answers. Thanks for watching.